So this evening we have with us um, Mr. Zane Scott. Mr. Scott's talks are always well received by our audiences across the Incose speaking circuit, and as such, he's really been a valued member and representative of our chapter here. Um, Zane is known as a prominent teacher, speaker, and blogger on a wide variety of systems engineering topics. And for those who aren't already familiar with Mr. Scott, he has a very interesting path through the systems engineering community. Um, he's well experienced with and trained as a hostage crisis negotiator, a mediator, and a labor management facilitator. He's taught communication, negotiation, and facilitation skills in a variety of government and commercial settings. And in fact, actually, we had him provide a tutorial on those skill sets as they apply to systems engineering discipline just this last March. Very successful tutorial. So he's a communication expert. Currently, he's the vice president for professional services at Vitech Corporation, but he also holds an associate systems engineering professional certification, an ASAP. This has allowed Zane to marry his broad range of skills with the principles of systems thinking and systems engineering while successfully becoming a leader in the systems engineering community. Mr. Scott was a member of the Incose Technical Leadership Institute's inaugural cohort. He's served as the chair of the Corporate Advisory Board and also as a member of the Incose Board of Directors. So with this introduction, I'm now going to turn over the virtual podium here to our speaker, Zane.
Great, thanks, Clinton. And it's great to be back with everybody tonight. I look forward to when we can do this in person and return to some sort of normal kind of a footing. Because if for no other reason, it means I get to make a trip and come and be with you in person, which I miss after having spent 15 years up there and then moved back to Blacksburg. I miss getting to see everybody. And I would mention that the end of the year holiday party at the Engineers Club is an event worth attending, even if you're not local. So I've traveled to that a couple of times since I've been back here, and it's always well worth it. Now, are you seeing my slides full screen?
Yeah,
yes, we are.
Okay, good. All right, so tonight we're going to talk a little bit about systems thinking. I'm not going to talk much about the how of systems thinking, and I see that you've got another program coming up next month where you'll probably get into more of the nuts and bolts and application, judging from the title. But tonight, what I'd like to do is to talk about systems thinking and to be just a little bit provocative if I can. So we're going to begin by just saying a word or two about what systems thinking is. And I'm drawing here from a very valuable systems thinking resource. Robert Edson, who's now with MITRE, when he was with ANSYS, wrote a primer for systems thinking called Systems Thinking Applied. And it's a great resource, a good little book with a fine distillation of the principles and aspects of systems thinking, and I commend it to you. I'll have a resource list at the end, and that's certainly one of the books that's in that list. We can boil this down with what Robert has to say here as being representative of systems thinking. And the focus in systems thinking is on the whole and not the parts. If you take one thing away, that's what you should take away about systems thinking. Because if we endorse and embrace systems thinking, then we should embrace the fact that we are called upon to take the systems view and to look and think holistically at systems. Now, we as systems engineers embrace it, at least on the surface. The game we talk is a good game with respect to systems thinking. If you look at how we define systems engineering, we define it as transdisciplinary and integrative in its approach. And we talk about using systems, principles, and concepts. We reach out and overtly embrace the concepts of systems thinking. So that means that we at least say that we think in systems. And we define a system as an arrangement of parts or elements that together exhibit behavior or meaning that the individual constituents do not. That's a sentence that's familiar to us all, and it embodies three different aspects of a system when we define it. The first is it has to be an arrangement. The second is it has to be made up of parts. And the third and most important is that those parts together in that arrangement will exhibit behavior or meaning that the individual constituents don't. Fritjof Capra wrote another book that'll be on our list at the end called The Systems View of Life. Capra is a theoretical physicist who's become an ecobiologist, and the common thread throughout his professional life has been the study of systems. And he reminds us that according to the systems view, the essential properties of a system are properties of the whole, which none of the parts have. And they arise from the interaction and relationship among the parts. He goes on in that same passage to warn us that if we take the system apart, either physically take it apart or take it apart in terms of the way that we think about it, we destroy its essential characteristics and properties, because those properties come from the interactions of the parts held in arrangement together. And that's all an essential setting for systems thinking. We have to think in that way. We have to think holistically and look at systems holistically. Now, from that, we take some pretty lofty goals. If you look at Vision 2025, the World in Motion document that Incose published in 2014, you'll find it embracing social and socio-technical challenges, if you will, on a global scale. So it talks about a role for systems engineering in dealing with climate and social problems like hunger and poverty. Those challenges rest on applying systems thinking and the principles of systems engineering to understanding those problems and solving them. There are other examples that come from some of our sister organizations and that we've looked at in Incose in selecting grand challenges. And if you look through this list, you'll see that these are not trivial challenges. I like the third one with a quote from Elon Musk, who says, "I want to die on Mars, but not on impact." But becoming a multiplanetary species, that goes beyond global. Delivering infrastructure, delivering clean water, delivering healthcare, reforming the education system. So there are lots of different kinds of grand challenges that depend upon applying the principles of systems thinking and systems engineering to problems that go beyond the making planes, boats, trains, automobiles, the kinds of typical engineering problems that we're familiar with. So we embrace this systems thinking. But do we really embrace it? And I'm going to suggest tonight that we really don't. That we say we embrace it, but when you look at what we do and what we think, we really don't embrace systems thinking. I'm going to talk about some of the reasons for that, and then I'm going to talk about its manifestations and some things that we can do about that. The first question is, why would I say that we don't embrace systems thinking? It's due to something that I'm going to call the paradigm trap. Coming out of the Enlightenment and embracing the scientific method as heirs to Descartes and Newton and others from the 16th, 17th, and 18th centuries, we adopted a traditional view of the way that science progresses and the way that knowledge progresses, not just in what we would call the hard sciences. And that is that we form a hypothesis, and then we raise questions, and questions come from outside about the hypothesis. And so we test it against those questions, and we learn about the hypothesis. And then we make modifications, and we re-hypothesize, and we move till we have more questions about the second version of our hypothesis. And we ask those questions, and we retest, and we re-hypothesize, and we rinse and repeat incrementally as science advances across time. Within that framework are our assumptions, the methods that we use, the language that we use to talk about problems, the language that we use to talk about solutions, the tools that we use to test, the tools that we use to examine our hypotheses. So that's our traditional model for the way that science advances. And the Enlightenment forebears of this were very much committed to the idea that this was a steady advance toward truth, that what we were doing was engaging in a truth-finding exercise where we incrementally moved closer and closer to truth. This went on for several centuries until in 1962, along comes Thomas Kuhn. And Kuhn says this incremental process is what goes on during periods of what he called normal science. And normal science used the assumptions contained within what he would come to call paradigms. And so the definition of the allowable questions, the definition of the tools that you can use to test, the definition of how you would go about advancing science was all contained inside the paradigm. And the problems that they came up against was that limited the questions. And so you would have people who would begin to ask questions that were outside the paradigm. And the first reaction of the paradigm, the people within the paradigm, was, you're not supposed to ask that question. You're not supposed to go there. You're not supposed to get outside of our assumptions and our ways of doing things. But those questions, particularly ones coming from outside, caused anomalies to be raised. And anomalies are problems that can't be at least easily solved using the accepted tools and methods. Kuhn himself, in his book, The Structure of Scientific Revolutions, said an anomaly is a phenomenon for which the scientist paradigm had not readied the investigator. So the paradigm had not made them ready to answer these questions, and they became anomalies. And Kuhn goes on to say, if the anomaly persists, it gradually becomes a crisis. And if that crisis persists, it can become a revolution. So as anomalies and crises arise, they could either be solved from within the paradigm. So normal science might solve them and they could be ameliorated. If they can't be solved in that way, then new approaches will be suggested. And if the new approaches begin to coalesce and actually come to some solutions, what happens, according to Kuhn, is a new paradigm develops. The paradigms exist side by side at first. And the problem with the paradigm is something that Kuhn called incommensurability. And with incommensurability, what's going on is the people in the new framework don't have the language to talk to the people in the old framework, and the people in the old framework lack the language to talk to the new framework. And so that creates a problem. And then you have the bed for a scientific revolution and the resulting paradigm shift. Now, there are numerous examples of these that Kuhn cites. In the world of cosmology, the shift from the Ptolemaic cosmology to the Copernican cosmology is just such a paradigm shift. In the world of physics, the shift from Aristotelian to Newtonian, and from Newtonian to Einsteinian, and then from Einstein's physics on into the world of quantum. Those involve paradigm shifts. They're not incremental journeys along the same path. They involve changing assumptions, changing methods and ways of looking at the problem. In medicine, the whole idea of germ theory, when that became a part of that science, there was a revolution and a paradigm shift. So within the individual sciences, you see these paradigm shifts. Now, when we begin to look at somebody like Russell Ackoff discusses the shift from the machine age to the systems age, and he discusses it without a lot of reference to Kuhn, in much the same way that Kuhn discusses paradigm shifts. In the machine age, you had the view that systems were deterministic. Cause and effect happened in pairs. So one thing caused another, and there was nothing without a cause. So you could trace backwards. So you could say, I've got D and C causes D. Well, what causes C? B causes C. Well, what caused B? Well, A causes B. So you go back as far as you feel like you need to go back to what they would call an atomic level. And that was your root cause. So this paired cause and deterministic lineup were characteristics of the machine age. And then gradually in the middle of the 20th century, early 20th century to the mid 20th century, you begin to have people publish things in several different areas, which created essentially an anomaly and then a crisis for the machine age. Bertalanffy's general systems theory contributed to that. Norbert Wiener's cybernetics contributed to it. John Dewey's work, Quest for Certainty, contributed to that, to the doubts about the machine age as a paradigm for talking about what's going on with systems. Heisenberg's observations about mass and velocity and direction and motion had a good deal to do with breaking apart our presuppositions in that area, and complexity, the whole idea of trying to deal with complexity. And so what Ackoff suggests is that the systems age, which it gets kicked off with all of these, the anomaly that builds into a crisis, results in a new way of looking at systems where cause and effect are non-deterministic. You're dealing with feedback. You're dealing with cause that happens not in pairs, but in loops. And instead of analytic thinking, like in the machine age, and Analysis, incidentally, comes from a Greek root that literally means to tear apart. And rather than tearing things apart in the new systems age, we put things together. We think in systems holistically. So rather than analytic thinking, we have synthetic thinking. And both analytic thinking and synthetic thinking become important, but it's not strictly analysis. The other thing is the systems age deals with systems in their environment. So you want to deal with the environment. In the machine age, we wanted to do away with the environment. We did our experiments in a laboratory. What's a laboratory? A laboratory is a setup where we've intentionally tried to exclude the environment. So we don't want to get beyond the bounds of the problem that we're testing and that we're experimenting with. But in the systems age, we do deal with the environment. Now, the result is that we're caught betwixt and between here. And why would I say that? What's the evidence for that? Well, we can find the evidence all around us when we look at what we're doing, from our language to our practice to the way we educate to our values. We see evidence that we're at least partially still caught in the mechanistic age. I didn't count on this, but I went to a presentation earlier today on systems thinking. And the presenter talked about analysis. She talked about coming from the big picture and going down to the individual parts of a system. She was talking about organizations and saying, if you want to influence the organization, you need to deal with the individual, who is the atomic level part of the system in order to have an impact. She said lots of valuable things, and what she was saying was true, but it was ignoring the systemic interactive parts. She talked about root cause analysis. Well, root cause analysis, as I just explained, depends on the paired cause, A causes B, that we get from the age of machines. Control theory. If you want to talk about control theory now, you'd be better off to think about talking in general terms. If you want to talk about systems on a broad scale, you need to talk about influence theory. How do we influence? Because in lots of systems and lots of environments and lots of settings, we can't control things. And so we're no longer interdisciplinary. If you go back and read the new Incose definition for systems engineering, you find that the fellows changed the word interdisciplinary to transdisciplinary. Their document is on the Incose website where they explain why they made the changes they did. And they have a real interesting discussion about why they went to transdisciplinary, because interdisciplinary implies that we have all the disciplines and they stay in their stovepipes and we talk between them. And in transdisciplinary practice, we transcend that. When you look at our practice, you see that we value process over principle. So we don't learn principles and then try to apply those broad principles to specific situations. People want a checklist. You know, give me a checklist. Tell me, if I do A, B, and C, I will be successful. That's what I want. Look at our process standards. Look at the Incose handbook. And the new edition of the handbook, thankfully, is going to be less process-centric than the old one. But we're wedded to process. Why? Because A causes B, B causes C, C causes D. So if you want D, you need to work through the process of increasing A, B, and C in order to get D. We fragment, we specialize. So in our practice of systems engineering, I interview systems engineers to hire them. And you'd be surprised at how many of them tell me, oh, I'm a requirements engineer. Well, that's great. And requirements engineers are valuable and they contribute greatly to our efforts. but they shouldn't masquerade as systems engineers, because there's way more to systems engineering than requirements. But we specialize. We specialize in architecture. We create roles. We want to have modelers. I want to have somebody who builds models. What you want to have are systems engineers. If you're talking about designing, maintaining, improving systems, you're going to need true systems engineers that transcend that fragmentation. It's in our educational system. Look at the education that we give to engineers. Look at the education that we give to various scientific specialties. You're specialized from the get-go. And we wonder why we do now survey after survey, study after study. And what do we find the deficiency is with systems engineers or any kinds of engineers or technical people? The deficiencies are in soft skills. Why? Because we take soft skills out of their educational path. I told somebody in the tutorial that I did back in March that I get the same feeling in the pit of my stomach when somebody says this is a soft skills course designed by engineers that I would get if you greeted me at the top of the stairway going into an airliner to tell me that this plane that I'm about to fly on was designed by a team of psychologists. Why? Because psychologists are not educated to do that. Engineers are not educated in soft skills. So it's no surprise that we've specialized and that we're set up to do that. We specialize with our tools. We specialize with what we call the practice. So we fragment. We say we believe in systems, and yet we act like we believe in fragmentation. We pay a price for that too. We get wedded to our applications, and we get so deep in our application that we can't see out to see first principles. I don't know how many times I've been told you can't do that in systems engineering. And the reason is that systems engineering is supposed to do this other thing, which invariably is the application that the person who's telling me that is most familiar with. We used a systems engineering tool to do process improvement in the intelligence community. And we had engineers who had used it to design equipment who would come by and say, you can't use it for that. That tool was meant to design things. That's because that was their application. But because they were deep in their application, they could not see out. Whose responsibility is it to see out of these pits, these specialization pits? It's the responsibility of systems engineers who are supposed to engage in systems thinking. So what's our ticket out? The ticket out is integration. The ticket out is to put it back together, to think holistically, to really engage in systems thinking by integrating. So the ticket out is integration. It's taking the systems view with regard to our thinking, to our practice, to our models, and to our tools. So what do I mean when I say, how do we apply it to our thinking? Well, we need to learn to think holistically about systems. And the best way to do that is building a framework that we use to think about systems. We need to have a framework that allows us to put all of the aspects of a system into its framework. In other courses that I teach, I talk about Charlie Munger, who is Warren Buffett's investment partner. Charlie Munger says we need to build a lattice work in our brain that we can put knowledge into. We can't just throw information in there. We can't just throw the elements of a system into our brains and expect it to stick and to make sense. We have to build a framework, and that framework is called a meta model, a model of the models that we build of the systems that we're going to build. When we apply it to databases and tools, it becomes the framework of the database repository in which we build models. More on that in a minute. We need to take the systems view in our practice. We're talking now about connected engineering, and we need to really engage in connected engineering. We need to practice our systems design and systems engineering together. We need to have the engineering disciplines at the table. We need to engage fully all the way through the life cycle with the different subject matter experts in engineering disciplines so that we can think about it holistically and not have a requirements table and an architecture table and somebody off doing this and somebody off doing that and a pile of documents that we contribute to. We need to think systemically and take a systems view of our models. So as we build models, we need to build them in a database that has that framework. And the reason is that we can put information into that database, and the database has a place to rack it up. It has a place where it goes. And that means that if we ask for the information back, so if we say, show me all the requirements, it can go to the place in that framework where the requirements reside and pull those requirements out. And not only that, it can show you the relationship of an individual requirement to the particular function that'll satisfy that requirement. And it can show you the relationship between that function and the component that'll perform that function so that the function can satisfy the requirement. All of that needs to be linked together in the model. So we need to have our models set up with that kind of a systems framework. We need to integrate with respect to our tools as well. So it's not really systems engineering if you have a requirements tool, and you have an architecture tool, and you have a drawing tool, and you have a tool for this and a tool for that. You can't say, look, I have all of these models. I've got a requirements model here, and I got this model there, and I have that model there. We're not thinking systemically at that point. So a bunch of different tools doesn't work. A suite of tools that houses a bunch of different tools is a little bit better step in the right direction, but it doesn't work either. And the ultimate thing that doesn't work is a pile of diagrams, whether they're physical diagrams or they're diagrams with data dictionaries attached to them that are not attached to each other, that you can't update in real time. You can't trace the effects from one aspect of the system to another through diagrams, this diagram and that diagram. That's not systems thinking either. Systems thinking says that if we're going to have a tool, it needs to have a model of the entire system so that we can have a systems view of the system that we're modeling it. And it needs to be able to produce the views out of that tool. And we need to be able to input information into the tool through those views so that they're integrated into the database. And we're really engaging in systems thinking. Now, why do we care so much about systems thinking? What difference does it make to us practically? Well, for one thing, it builds true understanding. I'm going to give you a citation to a talk by Russell Ackoff on moving from the machine age to the systems age. And in that talk, he talks about this, but when we think analytically, when we move from the system to the subsystem down to the parts at the atomic level, when we break things apart, what we gain is knowledge about those parts as we go down. So we wind up with a pile of knowledge but we don't build up understanding. We build up understanding when we look at the system as a whole, and when we look at the system in its context, and we look at that context in the environment. So we begin to think expansively rather than in a reductionist way. We think synthetically rather than analytically. And that's how we build insight and understanding for truly solving problems. The other thing is that our job as systems engineers, or even as discipline engineers engaged in design work, is to ultimately be able to say to the stakeholders, this design will fulfill the needs that you have that have driven you to ask me to design this. So we need to be able to make a prediction about the system behavior of what we're designing and say whether or not it's going to meet the requirements, it's going to fulfill the needs. In order to do that, the only way we can do that is to be able to see the whole system, to take a systems view. Why? Because as Capra warned us, if we take it apart, then we don't have any hope of knowing what its behavior will ultimately be. We destroy the essential characteristics of the system. Now, the other reason that we care is that once we learn to think in terms of first principles, we learn to think in terms of a systems view, then we can begin to transcend our particular applications. So we can begin to solve broad problems. A number of years ago, when Incose first began to say, you know, we need to be involved in the healthcare industry. That's true. Healthcare is a huge issue in our society, and systems engineering has a lot to bring to the table. But what did we then say? I know how we can be involved in healthcare. We could build healthcare devices. If I can build an avionics system, I can build a healthcare device. Pretty much the same kind of an application. All right. But healthcare devices, while they're important and they are a problem in the healthcare industry, are not the big problem. The big problem is healthcare delivery. Just go ask the people trying to manage the hospitals in India, or roll the clock back 9 months and ask people managing American hospitals. Is your big problem your instrumentation, or is your big problem how you do your throughput and your healthcare delivery? And systems engineering and systems thinking have things to offer in solving those problems as well. But in order to see that, we have to see beyond the orientation to things that we traditionally look at and begin to solve multidisciplinary problems, to solve socio-technical problems. So I've just really kind of pulled the scab off the wound and left it exposed. I've suggested some solutions. And so what I want to do now is suggest some resources for you. If you want to think more about this, if you want to look more about these different aspects that we don't look at every day, if you want to expand your thinking about systems thinking, here are some resources. The first is a set of 7 books. Now, these are by no means the only good systems thinking books. They are nowhere close to the number of systems thinking books that I have in my personal library. They're among the many books that I carry around on my Kindle now. Thank God for Kindle. It saved my back from running through airports with bags full of books. But these books are really good, I think. The first one that's there, and I've got them in the alphabetical order of the author's name, so they're not in order of importance or order of subject, is Systems Thinking for Curious Managers. That's a Russell Ackoff book. Ackoff has a great way of speaking and delivering and a great way of writing. That's an enjoyable read and an insightful read. And it's not about building things. The Systems View of Life by Fritjof Capra is possibly one of the 3 or 4 very best books on systems thinking and systems that I've ever read. Simple Complexity by Willie Donaldson. He was a speaker at IS, I think in 2014. And he talked about complexity as it relates to organizations. And that's what this book is about, is complexity and systems thinking within organizations. The Systems Thinking Applied by Robert Edson is the primer that I referred to. The Structure of Scientific Revolutions, that's not reading for the faint of heart, but it's very valuable. And if you want to see how that kind of kicked off the systems age, how that fits with work that was done by Berta Lanfey and others, read that book. Thinking in Systems, it's been updated a couple of times. It's a classic by Donella Meadows. It's a primer on systems thinking. And then the book that kind of popularized all of this when it first came out in '96, and this edition came out in 2006, is The Fifth Discipline by Peter Singh. So those are books, and I'm going to supply a PDF of my slides probably tomorrow morning back to Clinton so that you guys can have access to them. The other thing is I want to suggest to you 2 videos. One is a movie. Fritjof wrote a short story and then co-wrote the screenplay for this movie that was produced by his brother Bernd. And it stars Sam Waterston, Liv Ullmann, and John Hurt. Sam Waterston plays a United States Senator who's made an unsuccessful bid. Can't remember if he's trying for the nomination or actually ran for president, one of the two, and did not make it. And so he has gone to France to look up one of his former advisors and speechwriters, who's played by John Hurd. And he wants to talk about, what should I do? Where should I go from here? And they decide to go to Mont Saint-Michel and walk through that old monastery and cathedral on the island just off the north coast of France and talk. They do that, and very early on in the conversation, they encounter Liv Ullmann, who plays a Scandinavian-born particle physicist. And she is contemplating leaving her employment because she questions the morality of what her work is being put to use for. It's not Dirty Harry, go ahead and make my day kind of movie. It's a 2-hour conversation on systems and systems thinking. I think if you're in the right mood to watch it, you'll really enjoy it and get a lot out of it. The other is, and both of these are on YouTube, by the way. That's the entire movie there at that link, streams for free. And then the other is a talk. It's an 1.5-hour talk by Russell Ackoff. And it's titled From Mechanistic to Systemic Thinking. And Ackoff this is classic Ackoff. He's both entertaining and informative and challenging in his thinking. And it's a lecture that he gave back in 1993. So I commend both of those as well as the 7 books to you. And at this point, I am ready for any questions anybody would want to ask.
Feel free to unmute yourselves if you got questions you want to ask Zane.
Hey, Zane. Early on, slide 1, 2, or 3, I mean, it must probably 2 or 3, you sort of made a statement that indicated that systems engineering shouldn't be reductionist. but the sort of the rest of the talk and my experience doesn't exactly show that.
Systems thinking should not be reductionist. Systems engineering should not be exclusively reductionist.
I surely agree with the second statement. So, so how does systems thinking then remove itself far enough from systems engineering activities as compared to the concept of systems engineering that it does not do reductionism?
Well, what happens is that we're so much children of the Enlightenment, and we so subscribe to what we call the scientific method. So if we think that if we engage in synthetic thinking, if we expand the horizons, if we go to first principles, if we're moving up and out, then we must be doing something wrong because we have to analyze. We need to tear this apart. So my youngest brother was born to be an engineer. That didn't work out that way. But there was a time period in our elementary school days where you had to race home to protect your bicycle because he took apart everything. You gave him a toy for Christmas. We all three got toys for Christmas. My other brother and I played with the toys. He took his apart. And that's what engineers will do. So they'll begin to try to understand the functioning of the system by taking it apart. And as Capra points out, if you do that, you destroy the essential properties of the system. So to the extent that you're engaging in analysis, it's not a valueless activity, but it's not going to lead you to an understanding of the system.
Mm-hmm. Okay, I agree with what you've said, but it's more about the way we think about it than what it is and what needs to be done. So I sort of struggled with that for the rest of the presentation because it didn't exactly fit with my understanding of even for system thinking. When you go to change something, you don't change the system, you change the parts, and the parts that change modify the behavior of the system.
And actually, there's a great quote from Myron Tribus, who was a management expert. And he said, if you think you're going to change the organization by changing the individuals, you're going to fail and it's going to bite you. And you don't really change the system by changing the parts as much as you change the system by changing the relationships. So if in changing out parts, you change the relationships in some way, you may improve the system. But if you're just changing parts, you're missing the boat. And I understand that that's provocative because that's not the way we're trained. And that's not where we come from. And that's why we have the experiences that we do.
Okay, so so I was just listening to an article on the new Ford F-150 electric. Everybody probably heard that with Biden yesterday. So changing out the motive force for the car was not really a systemic change, since so much of the rest of the car is really still the same. It really is a functional unit of the car that changed, not the system.
Zane,
yes,
can I contribute to that one?
That'd be great.
Yeah, because the biggest problem with that isn't the car or the truck, it's the environment. That now if I buy that car, that vehicle, the environment has not been updated at the, what Zane's trying to talk about, the systems view of everything. So until that happens, the truck is, not as much.
Jim, you went on mute there somehow.
Well, I'm on mute. Yeah. I just went back. But it's just until you change the environment, the value of the component, so you've got to really look at the overall environment. And I have problems with that with my students, trying to get them to, perceive a system in the environment and the whole concept of validation. I keep getting people that really talk about design options and test options and really have a hard time understanding, getting back and understanding how the system fits in the environment at that larger systems thinking view.
So how do you partition then? Because I guess I would then say, so how does that fit into the rest of the universe, right? Because if you keep just saying you have to think bigger, you end up with a partitioning problem also.
But you don't have to model the entire universe, but you need systems thinking to reflect on the ideas that if you have secondary, tertiary influences that could change the way in which your system of focus operates, then systems thinking will help you by gaining that perspective and looking at the things holistically without trying to eat the entire elephant.
Well, there was a time, though, when we used to talk about families of systems and system of systems. So if you talk about, it's always, we have to look at it from the standpoint of perspective. And I guess the Ford truck is a good example of, you've got the president now involved, and there's a whole infrastructure that has to be updated to even support, at the vehicle level. They look at the truck as being a system. But, we always introduced this concept. I know in 2000, 2005, we talked about family of systems and system of systems to kind of distinguish that and make sure we were able to discuss it at the relevant level. So,
right, change of perspective. So, and if I could go back to the topic, I'd like to, Mrs. Fred Robinson, just to, I loved the talk. I definitely agree with a lot of what you said. The perspective that I'd want to add perhaps is, you talked about the doing of systems thinking, using the tools, using the techniques. There's also a couple of really interesting graphics out there. One of them is about the skills of a systems thinker. And so the doing of systems thinking, if you lead an engineer to tools, you don't make them think. They have to think outside of their tools. And so having and developing the skills of a systems thinker, I think, is really important. And I think one of the pieces of developing those skills is actually well characterized by the Waters Foundation, which is the habits of a systems thinker. And so, I forget who it was who was speaking, just started with the first question, but it's the idea of how do you take a systems engineer, and when they're doing the systems engineering, give them the skills and the habits of systems thinking to help them make their systems more reliable, more robust, better optimized for the conditions, et cetera. That's where systems thinking comes to play, in my humble opinion. Over.
And I think you're exactly right about that. And another thing that the Waters group says about that is that it's important that systems thinkers have a knowledge of the environment, of the context and the environment. And so you've got to be knowledgeable enough to understand how your system is going to fit into its environment and work. And we kind of emphasize the laboratory. So arguably the new Ford F-150 in the laboratory is just an F-150 with a different kind of motor. But out in the environment, it's not the same vehicle at all. And so we have to understand that. So we're interested in bringing things into our laboratory and doing our work in there and cutting the environment out of it. Our laboratory is clean and it's pristine and it doesn't have the environment interfering with things.
So when you
Josephine, go ahead.
So I just want to make sure that I'm understanding, and I kind of put this in the chat. Basically, everything will become a system of systems when you introduce it into the operational environment, correct? Because you have to take that into consideration as well. Okay, so I'm tracking. I would agree then with your presentation as well, right? So I've done testing most of my career, and dealing with the different engineers, the hardware engineers versus the software engineers versus looking at the system or being an advocate for the system, I definitely agree, because I think that when you're testing the entire system is when you get your first view of the entire system and how it operates in the environment in which it was intended, even though technically we're in a lab. But that's the first time you get the hardware and software married together to see how they interact and under what conditions. So yeah, this was pretty good. Thank you. I appreciated this. You definitely, it was definitely very thought-provoking.
Good. And Willie Donaldson has a solid agreement with you there. He has a great discussion of something called holons, which is a phrase that was coined by Arthur Kessler in a book called The Ghost in the Machine.
Oh, okay.
The concept of holons says that everything is a system made up of parts and a part of a larger system. So you don't think of the largest system that can be distilled down into smaller systems. You think of nested systems, like a stack of Russian dolls, and every one you unpack has systems inside it and is a part of the larger system as you unpack it.
Exactly. Yep. Thank you.
I think this is a very interesting discussion, and no one believes it's more relevant than a person who made a shift out of the aerospace industry over into the IT world. And if you take a look at system engineering, just job announcement, it gives you a different perspective as far as the tools, as far as the how the aerospace, the DoD, and the rest of the world looks at systems engineers and their role and the role that we play versus the IT industry and software industry and how it views the role the system engineers play as well. So very interesting discussion for me. One of the challenges that I've seen, and I think this is really relevant with the survey that was presented, is that oftentimes the system engineering groups and a lot of these corporations have been made up, it's been the catch-all for all engineers from all other fields, and they title them as systems engineers, but a lot have never been trained or members of Incose or even understand the tools and the roles and this attempt to implement system think within an organization. And that's been one of my largest challenges when I'm traveling
Totally
around,
agree.
stuff like that.
Totally agree.
Is that this talk that you gave, I'd love to have the slides for it, because I think this needs to be the opening presentation for every systems engineering organization to understand what system engineers do, what our role is, and how we fit into the organization. But I don't think that's been federated across the country, and there isn't a common understanding of it. And although Incose attempts to push it, when you get in the corporate environment, it doesn't exist.
Well, this goes.
Even in Incose, we push it, but then when we issue our handbook, the handbook is a process-oriented handbook. It focuses on the how and not the what.
But the principles, you made a good opening when you talk, because I'm sitting here watching this, I was holding back, like, wow, this guy, I'm seeing other people are experiencing the same thing I'm experiencing. When I've taken the Incose manual and tried to use it as an authoritative reference to say, hey, this is how the rest of the world does it. But a lot of times when you go into groups they've been established when system engineering was the catch-all, you have all these individuals that are not trained in systems engineering. And even when you try to use the Incose handbook manual, things like that, to at least say, let's have an authoritative reference as far as to what we're going to consider systems engineering and what the principles of system engineering are all about. You just get a lot of pushback when you go into a lot of companies, especially when I jumped over here into the IT world, as far as to accepting what you're pushing. And I believe it totally. I've drank the Kool-Aid as far as the principles as well as the practice of system engineering. But it's just a challenge a lot of times when you go into the organizations to really adopt exactly what you were pushing. Zane.
You're right.
So, hey, Zane, Dave Fadley, question. Hey, cool presentation. But I would also add by saying systems thinking is done, but it depends on your organizational responsibility. There's program system engineers, project, program, portfolio, and enterprise. And there's different systems, there's different thinking going on at that level. And I know as an ESEP, I've been across all those levels. And what you do is a lot of people start out at the lower levels just haven't experienced that, thinking broader. They think maybe one step beyond their little program, project, or part. But as they get experience in these other portfolios of organizational responsibility, you're kind of forced into do systems thinking if you're doing your job right, but not one all engineer does it all at the same time, at that level. So I would say it is going on, although at times you don't think of it that way, but it is going on if you've experienced different levels of system engineering in your organization.
May I make a comment?
Certainly.
Sure.
Zane, you said something up at the beginning when you talked about Thomas Kuhn's paradigm idea, that the old paradigm and the new paradigm are not communicating. They're using different terminology and what have you. And the systems thinking paradigm is different to the Incose paradigm. And the systems thinkers in Incose are not really communicating with mainstream Incose. And part of that difficulty to me seems to be that very few people have a way of actually teaching people how to apply systems thinking. This talk that you gave was really very good, but unfortunately, it's the same kind of talk that I was giving 20 years ago. When I was teaching at the University of University of South Australia, I was able to tell people about systems thinking. I could give them the benefits of systems thinking, but then I had to say, well, in about 20 years' time, you'll know it because you'll be using it. Bridging the gap from talking about it to actually doing it, that seemed to be an unbridgeable gap at the time. The other point I want to make is Ackoff wasn't quite right. Ackoff, and I will explain all that next month.
Yeah, that's a good segue, actually, Joseph. Dr. Kasser is going to be our speaker next month, and he's going to also talk on the topic of systems thinking and give his perspectives on the topic. And he's got an extensive experience as a systems engineer, I think over 50 years working as a systems engineer and educating as a systems engineer. So we'll look forward to hearing your perspective on this, Dr. Kasser.
And I would add that I agree with you, Dr. Kasser, in terms of bridging that gap. People very much want that gap bridged. When I went to law school, we would go into classes. And so you would go into a class on criminal procedure or a class on property law. And the professor began to talk about principles and philosophies, and you would look at historical evolution of ideas and all these things. And most people in the class were very frustrated by that because they'd say, hey, look, I've got to go to Podunk, Tennessee and practice law. What use do I have for all this philosophy junk? And you need to teach me how to find the clerk's office and how to file a pleading. And when do you teach me that? And it took me most of the 20 years that I was in the practice of law to realize why they did what they did and the wisdom of doing it. And that was that I could get into the courtroom and I could beat the guy who had thought about this application and that application and this application over here, but didn't understand the principles that tied all that together. And they wanted to insist on, this is like, they wanted to make analogies. This is like that. And they wanted to leap from one to another and use the same language and the same terminology and just talk about applications, but not about principles. And when you combine that with the world that I've seen is my whole world, kind of an outlook. So if I came from the software world, I think that it's not unreasonable at all to go to a hospital administrator and show him a bunch of UML diagrams and think that I'm explaining a system to him. I'm not. And when I try to speak compartmentalized language or to distill things to a punch list, people don't want an education. They want training.
Yep.
They don't want to go to school to get an education and then go out into the world and apply it. They want to go to a very difficult vocational school and then go apply what they learned in vocational school.
Well, I would expand that a little further, though, to say that corporate America hasn't adopted the principles of systems engineering. You know, and you give an example of law school. Black's Law Dictionary is recognized as the common glossary of terminology for law. If you go into a courtroom or whatnot, you're referencing the same glossary. We don't have a common glossary within corporate America that matches that of academia. We have so many people that graduate with systems engineering degrees. And I started the field of system engineering before it was a degree. Now we have 95 universities. When I first started it, you couldn't get a degree in systems engineering, just a function. Now it is a profession. But I don't think corporate America has adopted it that way, to where you have a same set of common tools, a set of common principles, to where we can at least base the actual profession of system engineering on. And I think I loved your presentation, but I think there's one little piece that when you highlight the dichotomy between the two, but I think that to me is a glaring issue. Since the 25 years I've spent in system engineering, there's really a big gap. The different corporations that I've worked for or whatnot, the corporations have not adopted the role the system engineering is going to play and adopted this whole concept of system think, and then bring us in as systems engineers to implement or put the tools in place so that we can manage this complexity.
Yeah.
How do you expect that to happen
Yeah.
if you can't get the systems engineers to agree on what systems engineering is?
Right. Yeah. I was going to comment.
Well, I think we
that.
at least have a base agreement. We've got 20, 30 years of, Incose started that in Incose and switched over to Incose. We've got bodies like this that actually come together to where we at least have a base agreement upon things like even the terms. We've established a body to where, now the intricacies, we still have a lot of issues, but I'm talking about just the whole function and the real big key. And I think this was the first one in the survey of are they implementing system engineering to manage complexity? Everybody's realizing this is a big challenge. That's why you see the medical departments, the injury departments, everybody now jumping on board. Within the DoD and the aerospace industry, we realized this 20 years ago. But now they're realizing that this is the tool that you're going to need to manage all these various complexities. And we have at least a base agreement upon some of the principles, and also this whole speech about system think, as you said, you could have given this presentation 20 years ago. So everybody's established that there's a need for it. We at least have some of the principles. We have the Incose manuals, we have requirements writing guide, we have a UML, this big push with SysML, model-based system engineering, the new big buzzword and stuff like that, but people don't know what to do with it. That's what I've been experiencing myself. And then when I even try to use authoritative references to get people to agree, to say, let's agree upon at least some of the principles that we've negotiated on and thought about that academia is working on, and try to implement that actually in corporate America, that's where we have the big challenge.
This is Shirley. Can I
interject, Shirley, a second?
Okay.
I'm going to leave the room open for discussion, but I want to sort of finish up here with the talk. We're a little bit over our normal scheduled time here. So I want to first thank Zane, if I can share my screen here. Okay, just share my our appreciation with you, Zane, for doing the talk tonight and helping the chapter out, and we've had some very good discussion because of the talk. So I just want to formally thank you, and then I'm going to ask Dave Aldridge to if he wouldn't mind doing the raffle get the raffle wheel up. We're going to raffle off here a vintage caffeine delivery system. It's the official Incose caffeine delivery system. So as soon as Dave gets the wheel up there, thank you, Dave. Go ahead and spin it. And the winner
is Ross Henderson.
Ross Henderson, congratulations. So, Ross, I'm going to use your email that you registered with to contact you for mailing the caffeine delivery system. So, thank you very much, everyone.
Awesome. Thank you.
Yep, you're welcome. And I want to thank all the non-local folks who went out of their way to attend here. I know we really got people from all over the world attending. That's really great. A lot of good diversity and input into our discussions. So I'm going to leave the room here up. If you want to stick around and chat a little bit, feel free. Zane, you don't have to. If you want to stick around, it's up to you. Although,
Clint, this Kaz, are you going to do the picture?
Oh, yeah, I forgot about that. Everybody who's left, turn on your cameras, and we'll get a picture for the books, record books, or whatever. But what I was going to say is, if you show up early, the meeting's open normally at 6 o'clock. And so that time between 6 o'clock and 6:45 is meant for membership networking and discussion and such like that. So if you want to
I wasn't able to get in. I sent an email. It wouldn't let me in.
How did you?
I tried
Well,
to Zoom.
at 6 o'clock, there was an issue with getting things started.
Yeah. So
if you tried at 6, there might have been an issue.
I think.
Well, I tried a while, like for 10 minutes at least.
How did you get in then?
So the meeting opened up to me. Maybe I only signed up for the presentation. I don't know, because the last time I was able to join at 6 for the business meeting. Right.
It didn't come online until about 6:20. It was about 6:20 before the meeting actually opened up.
So there was technical issues. So
the
way that you were trying to get on was the correct way, but I had some problems setting up the meeting, and that I think was probably what was preventing some folks from getting in. So I'm sorry for that.
Okay. All right. I just didn't understand, but I was here.
Okay. That's great.
Thank you. Thank you.
We recorded your attendance too. Don't worry.
Okay, thank you.
And make sure your picture shows up.
Yeah.
Oh yeah, get your picture.
No, I didn't. My hair is already out all over my head. So next time, I'll plan for it next time. I promise.
Okay.
We'll do what I do, have a photograph in there. So when I turn my video off, it shows my picture.
If you turn your video,
watch.
I've seen people do that, so I'll have to doll myself up and get a picture. Maybe I'll try that.
Yeah, I think you have to add. I don't know how to do that actually. I have to look at Zoom to figure out how to do that.
It's just like you do any other background. Just
is it? Is that where it is?
Take a selfie and then you can pop it in
there. My avatar. Yeah.
Okay, so set up to take the picture.
Oh, I think they took the picture already.
Okay.
We've got
I'm sure I was yawning. I'm sitting here trying to smile. Did you guys do the picture already?
Well, actually, we're recording. The whole thing is being recorded.
I know.
We've got lots of pictures.
How about we do a quick countdown and then we'll get back to it. So ready, everybody smile. 1, 2, 3.
Cheese.
There we go. We've got it now. Thank you, everyone. So Clinton, did you want to keep this open and let additional conversation flow freely?
If anybody has any more questions or material they want to bring up, feel free. Otherwise, we are done with tonight's presentation.
I
Or
think we
just-
should pick this up again in a cafe format at IS. I think
That's
everyone goes
really
and
good.
thinks
That's a great
about all
idea.
this, right?
Yeah, I
And then
agree.
we pick it up
Yeah,
from
that's
here.
a great idea.
Well, no, there is
It would be
a,
a great segue for the next meeting also. That's
Yeah,
a really great
like I
idea.
said,
Right, for the
show
social
up at
hour.
6,
Yeah.
and we can have that those discussions then too.
okay, and do note that at the IS, and I think even at the IW, there's a like a systems thinking roundtable that they have where the people kick around ideas. So, and I think that was hosted by, oh boy, I don't remember her name. She's from Norway, I guess. I think it is.
Seal?
Usually Susan.
Say again?
Yes, Cecilia Haskins.
I have
Oh,
a,
yes, there you go. Yes,
I think I got this as,
you know.
I got this as some feedback to some of the statements that I made with regard to, we do have some practice manuals, as mentioned. When we talked about the requirements writing guide, the, you know, this is a principle manual or a principle topic. And does Incose publish anything like that to talk about the principles of systems engineering?
Nope, not as far as I know.
So in the competency framework, it turns out there are a lot of principles because of the knowledge that has been captured in that framework. Have you looked at the framework yet? What's being put together now is the assessment guide for that, and it should be published later this year. And one of the tracings that I'm volunteering to do is between the handbook, which, as was said earlier, process-based, right? And the competency framework, which has embedded within it a lot of principles and the knowledge and understanding and that taxonomy continuum that has been remarked on tonight and was put in the chat. So stay tuned and then join the working groups and contribute.
Because I think, you know, understanding, I think, is made up of knowledge plus context. And I think the principles provide that context, you know, and we have a lot of knowledge out there, but the principles kind of sew things together. And Zane, thank you for your analogy to the legal profession. You know, I think that was spectacular with respect to, you know, zooming in on the challenges that we have within the system engineering profession. And that having that context, you know, everybody wants to know the knowledge, you know, but not understanding the application. And as you stated, a good attorney can go into a courtroom and crush an opposing attorney if they understand the context of how things were developed and things of that sort. So I think that was great.
And we all, as a system engineers, that we could crush the dissent in our meetings as well. So,
well, we wish, well, we had the references, you know, the nice thing, it'd be great as system engineers, we had the real authoritative references, because that's my challenge in a lot of these corporations I go into, and I'll go in and there'll be a bunch of system engineers in there, and I'll be the only one that's really trained or have experience in real systems engineering. It became the catch-all for everything else. And then when I come in and I start talking about these principles, I can talk about the process stuff. When I start talking about the principles, that's when you kind of lose people. So having authoritative references about the principles would be great, because I haven't been able to go in with a book and say, hey, go read this. That doesn't work. But if we had some context.
It's what I think of as the Butch Cassidy and the Sundance Kid model. Remember, they get into a fight, and one of the guys says, wait a minute, what are the rules? And the other guy says, rules in a knife fight? No rules. And that's kind of how we operate. You know, I can't appeal to authority because nobody uniformly accepts the authority.
And we get stuck in storming. You know, and one of the key things that we as system engineers try to do is to normalize things. But if we can't even normalize our principles and our practices within the group, then we get stuck in system engineering in our own internal groups storming.
Well, if you look at all the different textbooks on systems engineering, they all cover totally different. There are a few common elements and the rest are all different. And I did a study a few years ago on master's degrees in systems engineering from 10 universities. And I found that 2 of the universities, you could get a degree in systems engineering without taking a single required course in systems engineering.
Where's that?
Where's that? I don't remember, but it's published in one of my papers, and
I'm
that
just
got me.
joking.
That's all right. It got me banned from presenting at the Incose Symposium for 2 years.
So, hey, Douglas, this is Dave. I think, and I also worked in DoD aerospace, then went to IT world, right? And I saw the differences in what they called SEs. Some of them, system administrators were called SEs in the IT world, right? And yet when you're sitting there and trying to, hit a bullet with a missile, it's the opposite end of the spectrum of hardcore system engineering, right? Which I grew up on. And so what I found is very domain specific. It's what is emphasized, right, in that domain, whether it's a management, the program, what the objective is, is schedule important, is getting 10% capability important, is reliability important, like space, right? And to me, that's where the system domain aspect comes into what you can call it systems thinking, what's important in that domain, what's critical for that organization, right? I teach classes, I always say, I always say, assess your environment you're in. Assess the environment, your domain that you're in, and your organization. What's important to them, and then pull the tools out of your toolbox as an SE and help that organization do what's important to them. Obviously, you don't go to extremes, being unsafe or unethical. You don't want to go that far, but that's what I found is you kind of have to pull that out. So Kosikov wrote a book. I think it was Principles and Practice of System Engineering, which was fake, based on missiles and DoD and that kind of stuff. Which was good, but it was very specific domain for that.
Yeah, but I think also it's fairly new too to the IT world, so it's going through its phases. I remember back 10 years ago we had this big push to shift left, because all we were doing was creating what we used to call shelfware. A lot of the documentation stuff like that we was creating, because the way we was reviewing requirements were really just shelfware. Nobody was using it to really ask the question of what. It was instructions on how to do things, and we had this big push back then to everything needed to shift left. And I haven't seen the IT world is still just assembling. They're not designing, if you ask me. They're putting parts together. They're putting components together in pieces and stuff like that. So they haven't made the shift left for requirements to be asking the question of what we're doing. They're still writing documentations to how we do things. So.
Yeah, well, a lot of the software is kind of show me the rock. Build me something, I'll tell you whether I like it or not, right? Versus here's my vision of what it should be. Now let's get there. It's the nature of that domain, right? We just have to shift as SEs, knowing what our domain is. That's what I found anyway.
Yeah, I agree.
You mentioned a moment ago the Systems Thinkers Toolbox. What do you think are the two basic tools that should be in the Systems Thinkers Toolbox?
I say understand your problem, understand the domain you're working in, understanding what the true problem is you're trying to solve. That's a number one. I don't know, a number of things, but I think that's probably before you do any engineering or anything, you got to do those things.
But what do you use to do those things? What are the tools?
There's a number of tools. I think all the tools we have in our toolbox, whether it's digital, whether it's PowerPoint slides, whether it's Excel spreadsheets or whatever, depending on what you're doing, you can do those things. I've used a number of tools over the years, and many organizations use a number of tools. They all can work, again, depending on what they're trying to accomplish and what's important to them. That's what I found.
So you're talking physical tools.
So intellectually, I would say a ConOps, right? Wouldn't that be a starting point for a system?
Yeah,
or how
defining what the system must do. Yeah, the concept of operations.
Right.
What if you don't know yet? I run across, they don't know yet what, they have a vague idea what it's going to be, but they say, well, as we go along, we'll evolve it. After we build it, we'll figure out the details of how we're going to do this stuff.
And that happens when you're working in organizations where they're pushing technology. And that's always the argument. We don't clearly understand what it's supposed to do, but there are a number of papers and things like that that's been written that push back against that attitude, to where you don't know what you're going to do. You do have some concept as far as what it's supposed to do functionally.
Yeah. My answer is, well, what do you think you're going to do with it? What problem are you trying to solve with it? That's kind of how I start with basics, and then get them talking with that. Otherwise, why are we even doing it? So if you can't answer those questions, why are we even here?
Yeah. Yeah, if
Because
you
we
don't,
got
if you
a
don't have
pot
a
of,
problem,
we got
what
a
are we
pot of
trying to
money.
solve?
We got a pot of money. That's why.
Yeah, there you go. Yeah.
Yeah, that happened to me too. Here's $20 million in 2 years. Do good things in space with this stuff. I had that problem too. And that was the most fun I ever had, by the way, figuring that one out.
But in moving around and talking with engineering audiences, one of the things that I get back a lot is that engineers feel like they're not given the dignity of being considered a profession. And so, you know, what are we doing here kind of is a question. And I tell them to turn to the traditional professions and take a look at how they're prepared. You know, I wanted to be a lawyer when I was 11, 12 years old. And when I was getting ready to go away to college, I went to talk to the dean of the law school at Washington Lee to ask, you know, what should I take? How should I prepare myself? Because I understood clearly that I was 7 years and a big exam away from being considered as a professional. And he said, no law school, no law courses, no legal preparation at all as an undergraduate. You need to learn how to think. You need to learn how to communicate. You need to learn how to write, how to speak, how to read and understand, how to do research work. Those are the tools that you have to acquire in that first 4 years. So take something that's going to make you write and speak and think and research and learn how to learn. Then come to us and we'll start giving you the tools of your profession. But when did you as engineers take your first engineering course? First semester freshman year. Start right in with the vocational type courses. And what that leads to, I think, is a failure to understand the scope of the world, the lay of the playing field, the ability to understand and diagnose the problems, see the implications of the problems from one domain to another. You know, to be able to learn how to innovate. All of those things are missing because, and if you say to an engineer, I think you ought to go at your education that way, they'll go, oh my goodness, I can't wait 7 years. Who could wait 7 years to actually be able to practice their profession?
Well, look at what they're trying to cram into an engineering degree now. It's almost a 5-year diploma now. So you have to start with the mathematics, the science and stuff like that in your freshman year to even once you get to the application level, you got to have that foundation. So what you're stating is a total restructure of, you know, engineering program. And
in a sense, yes.
Yeah.
Let me give you I teach this, but let me give you the analogy of how I teach it. If you think about mathematics, mathematics is split into pure math and applied math. So what you just described about law was the pure law and then the applied law. And it's the same in systems engineering. From my perspective, we have pure systems engineering, which is the systems thinking and problem solving aspects. And then we have the applied systems engineering, which is requirements, architectures, V&V, and so on. And yet the whole focus of Incose is on applied systems engineering, and there's very little on pure systems engineering.
And
that's what we get paid to do, though. We get paid to apply the theories. We don't get paid to think.
True, but we need to understand the thinking.
Well, one thing on Joe, one thing on system engineering, we've used and I've learned over. I don't remember who originated this, but you know, in the problem domain, it's like there's problem domain and there's solution domain, right? And you can almost think of the thinking. A lot of thinking has to go on the problem. You know, what a problem we're trying to solve? What's all the data for that problem? You know, all that stuff, and defining operational requirements. All this stuff apply up in the problem domain to finding and describing the problem to be solved. And that can be almost like the pure thinking aspect. and the applied would be on this, on the solution, requirements, test, validation, design. That's all coming up with solutions, and the whole DoD stuff, with their analysis of alternatives, trying to get people to think, right? Come up with non-material solutions, doctrine, training, all that other stuff. I forgot the acronym. It's like 7 different things, right? To go figure out before you think about even designing something, right? It's supposed to happen. Yeah, how well it works, I don't know, but at least people have put thinking in here to say, look, don't jump to solutions. Which is what engineers are trained to do, is jump to a solution. How many times you go in a meeting within 10 seconds, everybody's gone way down in the weeds to talk about how to go do what solution it's going to be. That's pretty typical because that's how people are trained in engineering. I mean, I came out with 2 degrees in double E. That's how we were trained, right? It's only on the job that I learned, hey, there's broader, you got to understand the problem first and all the stuff that goes with that. Maybe in grad school, maybe that's more things that I think you can learn principles, but then you got to practice it doing it on the job too. So
I was in a very interesting discussion on AI at the IS last July, and they were talking about algorithms and the design of AI, and they said, what do we do when an artificial intelligence run system is confronted with a choice that has moral or ethical implications? In other words, what if the self-driving car is confronted with a choice of either driving out of the road and endangering your passengers or driving head-on into a school bus full of school children? How does the algorithm decide what to do? And I'm sitting there going, what's really frightening is the algorithm was designed by someone who never heard of Jeremy Bentham, never heard of David Hume, doesn't know what utilitarianism is, has never heard of the trolley car problem. This has all been gone over and discussed in all its dimensions in the 1700s.
Right.
But the people designing AI, how much ethical philosophy do you have to take to be a software designer?
Right. And so Zane, maybe a system thinker would say, hey, an AI is a solution, but is it the right solution for a certain problem you're trying to solve? Right.
Exactly.
That's where the system thinking comes. Don't just jump to AI, guys, as a solution. What problem are we trying to solve? And maybe that's one of the alternatives, and maybe it's not. Maybe there is a moral ethical component. That's not the right solution to put in that problem space, right? To solve that problem. That to me is the way system thinker should be doing on that.
Maybe you don't need to fix the algorithm. Maybe you shouldn't put the algorithm in that position in the first
Correct. Right.
Okay, folks. A lot of great discussion. How about we continue this maybe with next month, and I'm gonna maybe close up tonight's event for everyone.
Actually, good old days,
This
guys.
was really good. Yes, thank you. This was excellent. I appreciate it.
Thank you, Zane.
Well, it's really good for me to come to these types of meetings and deal with like-minded people and see that people are having the same challenges across the universe that I'm realizing in my little world. It's a system of systems problem. Gotcha.
Don't forget that there are also 3 cafes that happen twice a month, about every 2 weeks. There's one that's set up on a time zone for California and Asia, one that's set up for Eastern US and Western Europe, and then another one that's set up in a time zone for Asia and Australia, if that's correct. So it's a Maple, Fir, and Oak cafes.
If we're encouraged, these are cozy cafes.
Good remember.
Yeah.
Good reminder, Bruce.
Yep.
Thank you.
All right, all.
Thank you guys
everybody.
again. Have a good night.
Good night, all.